Um, and I think next time we'll discuss Fry probably. And then maybe Growth 16 and its predecessors. Really, its predecessors. I don't typically cover the full details of Growth 16. And then Recursion and Nova, and then that'll be it for this run through of the reading group. And so today, it's particularly bad to be sleep deprived today because I'll be kind of free associating, the content about ZKVMs, which is sort of a looser topic than typical. If it's Fry, I know exactly what to present, and today it's less clear. Let's talk about this. So a ZKVM is a snark for a particular kind of statement. It's lets a prover prove it correctly ran a computer program on some witness. So let's say the witness is committed at the start of the protocol. Okay, where the program is specified, for, let's say, it's a computer program for a particular virtual machine model. So to be very precise, it'd be specified as bytecode. That's sort of like machine code, a description of machine code, that an actual CPU might execute as bytecode for a specific virtual machine. And this just means a particular CPU model. So, people, at least in ZKVM world, use the following terms interchangeably: virtual machine, CPU, instruction set architecture. Just a description of a simple computer. Okay, so that's what a ZKVM is. It's a snark that lets the prover prove, I correctly ran this computer program, specified as bytecode for specific simple CPU. I ran it, cycle by cycle, and I did exactly what the program was supposed to do every single cycle.
And this is like a deterministic procedure. There's like one exact correct way to run the whole program, right?
Yeah, that's right, because CPUs are deterministic. So once you fix the witness, which is like the input to the program, there's kind of one correct way to run the program. Now you could imagine, the computer program implements some kind of randomized, procedure to check the witness in some way. And in that case, that still works here. You would just treat the randomness used by the computer program as, being supplied by, let's say, the verifier, and then Fiat Shamir would actually let that be, prevent any interactivity in the snark. So, this notion of there's one correct way to run the computer program, I think that's fine to have in your head. And it's not actually limiting, right? Like, that still lets you run computer programs that themselves make use of randomness. Was that a clear response?
I actually feel like you made a distinction there that I wouldn't have thought about. But you're saying the programs are allowed access to randomness, so there isn't necessarily I guess it's not entirely deterministic, like what the correct program procedure will be.
Yeah, sure. Like, you could have a computer program that, what's a common example? Let's say the computer program, takes as input three matrices A, B, and C, and wants to check whether, A times B equals C. And the way it does the check is by running Friedwald's algorithm, which picks a random vector and just checks, does, A times B times that vector equals C times that vector. Okay, there's no problem with, the computer program running Friedwald's algorithm. The fact that Friedwald's algorithm is randomized, it doesn't really matter, right? Because what you do is you basically make the prover choose the randomness to use within the randomized algorithm via Fiat Shamir. And so it's fine for the computer program to itself be randomized. We have ways to deal with that. Is that yeah? Okay. Other questions? Okay, and so I think the reason people are so excited about ZKVMs is largely kind of a usability or developer experience benefit. The whole procedure, the way people used to do things and still do to a large extent today, is if you want to prove you correctly ran some computer program, you basically kind of hand specify a circuit, or if not literally a circuit, then you'd code up the computer program in some ZKDSL, which is often a very low level language, and it'd be a giant pain to take the computer program you actually care about and implement it in this very low level ZKDSL. And even if you managed to do it, it'd be probably full of bugs and all. It's just not a scalable process. So with ZKVMs, developers can write computer programs in whatever high level language they like, be it Rust or what have you. They don't have to know anything about snarks and how they work. They can just apply a standard compiler to compile the Rust program down to bytecode for the VM we have a ZKVM for. You do need to make sure that that compilation procedure from the Rust program down to the bytecode is correct. Because otherwise the ZKVM is going to let the prover prove it correctly ran the wrong bytecode. So you have to be aware of that. But assuming that developers manage to get correct bytecode, then the ZKVM lets a prover prove it correctly ran that bytecode on some witness. And the point here is developers just had to know how to write Rust, and that's it. So it's mainly a usability thing, and I'd say the challenge is, so the benefits are usability, and like maintenance, right? Like if you change the computer program you care about a little bit, that would be a massive ordeal if you have a giant CIRCOM implementation of that computer program, and now you have to rip out half the CIRCOM and replace it. Now you just change the Rust code to incorporate those changes and recompile to bytecode, and you're done. And the downsides are performance overheads are very high for the prover, and the ZKVMs, like the implementations are just extremely complicated, and so they're definitely full of bugs. Now I don't think it's necessarily any worse on the bug side than the old way of doing things, just because even if we implemented Plonk correctly, which still I wouldn't have high confidence in, the constraint systems the circuits people feed the Plonk are likely full of bugs. And so similarly, our ZKVM prover implementations today are definitely full of bugs. And there's a major effort to bring in formal methods, formal verification tools to try to get rid of all those bugs. So that's sort of high level ZKVMs. I'll pause again, see if anyone wants to ask a question. Okay, so there's still quite a bit of diversity in the VMs people target. So for sure, the most popular at this point is RISC-V. So I view RISC-V as just the simplest instruction set, the simplest VM that was designed, by the computer architecture community. So there's existing infrastructure, there's existing compilers from like Rust to RISC-V, things like that. And so I would say, the popularity of RISC-V is because it's the simplest, VM, that like already existed before, that already existed, before the ZK came in. Right. And so, there are many benefits to using an existing VM. For example, you get to just like reuse, like use existing tooling off the shelf. We can, just use existing compilers from Rust down to RISC-V. Snark people don't have to write their own. If you write your own compiler, well, firstly, you have to probably hire some compiler experts to do the work. Secondly, you're even more likely to introduce bugs because, you're doing stuff from scratch that hasn't been subjected to scrutiny and that, there's a smaller community looking at and all sorts of things like that. So major benefits to using existing tooling. And RISC-V is just kind of the simplest thing that has existing tooling. So it's the natural thing to start with. I don't necessarily think it's sort of the be all and end all. Other projects have considered like WASM, and let's see, MIPS, which is very similar to RISC-V. So these are all existing VMs that Snark people didn't design. At the other end of the spectrum, you have VMs that Snark designers designed the VM to be Snark friendly. And so these are things like Cairo, Miden. I guess Velita is RISC-V inspired, so it sort of lives actually. Maybe I'll put it in between, and there's like a spectrum, and Velita would be in the middle somewhere. And I share my personal opinion because I'm not shy about that these days. So my view is that if you design any VM with the goal of it being Snark friendly, right, what you actually wind up doing is making it friendly to today's Snarks, which have limitations that are artificial and will not remain, tomorrow. And so you wind up, in my view, sort of optimizing for artificial limitations that ultimately it's sort of a net negative. Like not only can you no longer use existing tooling because you just invented a new VM that there's no tooling for, but I actually think it's worse for performance. And what you sort of wind up with is kind of every cycle of like the simple Snark friendly VMs like kind of does less useful work than something like RISC-V, right? Because the primitive instructions are simpler, or it has fewer registers, or something like that. But then it sort of turns out that through some magic, almost miracle, that the same instruction sets that are good for real hardware like RISC-V or whatever are actually just as Snark friendly as the instruction sets designed to be Snark friendly. And so you wind up basically with requiring more cycles to do the same computation because each cycle does less useful work, but then each cycle is not actually any faster to prove because these are not actually any friendlier to Snarks than something like RISC-V. This is obviously a highly opinionated, my personal view. And so, I think, we're going, RISC-V is not the be all and end all, but my guess is if we move in any direction at all, it's kind of to go further up in complication. And, I don't think we'll ever be, a ZKVM for, the latest Intel chip or whatever, but, we might be somewhere in between the complication of RISC-V and, whatever happens on Mac, Apple Silicon or some Intel chip or something. Okay, so that's the VMs people target. And so now I'm just going to tell you how I think about a VM like RISC-V, and of course, something like Cairo is reminiscent because Cairo was inspired by actual CPUs. It's just, simpler in various ways than RISC-V. So a CPU, a VM, like what it does is it repeatedly over and over again calls fetch, decode, execute. All right. And so, one cycle is fetch, decode, execute. And so, running a computer program just means, calling this fetch, decode, execute some number of times. Say, do that, I use capital T to denote the runtime of the program. So say T equals, I don't know, a trillion times, just as an example. Okay, so I'll unpack momentarily exactly what fetch, decode, execute means. Let me just pause yet again, see if anyone wants to ask any questions. Okay, Abby, confirm I'm still.
There's a question asked, what are these VMs limitations?
Oh, like something. Okay, so I can tell you Cairo, just because that's the kind of snark friendly one I've looked at the closest. So it only has like 2 registers. Versus like RISC-V has 32. It has a very small number of primitive instructions. I don't want to get the number wrong, but it's under 10, I think. I don't know the exact number off the top of my head. Okay, and the primitive instructions are themselves designed to be snark friendly. So I believe defined as with finite field arithmetic. Right. So like if you look at something like RISC-V, like, you might have 2 32-bit data types X and Y. And in RISC-V, if I call the add instruction, right, like this basically computes like X plus Y modulo 2 to the 32 or something like that. Right. So it just adds them together, and there's if they overflow into a 33rd bit, it just throws it away or something. Right. What Cairo does is it will just add X and Y in the field. So let's say if it's a prime field, like just mod P or something. And that's meant to make the VM, like more easily implementable in Snark land, where everything works over finite fields. But, now you have a discrepancy between the computer program, like the Rust program you actually wanted to run, like doesn't have any notion of arithmetic over this field, but that does, have, int data types, or, UN64, UN32 data types, which more closely corresponds to, RISC-V edition or something. So
isn't it possible that there are just sort of certain types of problems that are better for one type of kind of instruction set than the other? And so, yeah, it may turn out that like the types of programs that we write in Rust, or like the way that we kind of think about the programming model in Rust, performs well for the RISC-V, but there are other situations where it is the like Cairo that actually is more suited to the problem.
So yeah, so that's possible. I think it's extremely rare. In that, look, what these. Cairo was designed in, I don't know exactly what year, but several years ago, right? So the snarks at that time, like, they basically could prove like circuits over finite fields, air constraint systems over finite fields. What those basically are straight line algebraic programs. Okay, so that means like no loops, no branching, just like plus and times over finite field, predetermined exactly, which sequence of plus and times operations, everything over a finite field. Okay, I mean, that just doesn't really capture anything. And if you look at some of the, it doesn't directly capture anything, right? So if you look at some of the sample programs, like I was doing, so it's probably been a couple years now, for some of the snark friendly VMs, right? They're all like made up stuff, honestly. It's like Fibonacci, but where Fibonacci, the arithmetic is defined over a finite field. So it's not even, like Fibonacci that, it's not even real Fibonacci. It's finite field Fibonacci. Or it's like computing the first X prime. Yeah, it's some artificial version of the problem. Compute the first X primes, because X is, you're just not going to overflow your field, if X is less than, some bound, and right, and like the sample program only goes up to that bound, so you just never have to worry about overflowing the field modulus, right? So
is kind of like, is just abstractly though, like if we kind of design a snark friendly instruction set, wouldn't that like allow what but so far we've only been thinking in like an older or like a different model. And you're kind of comparing like the performance of VMs built on top of RISC-V instruction sets now against things like Cairo, which, like you said, were started years ago and like are limited by bad, like maybe decisions they made previously. And whereas like if they were to start from scratch with snark friendly like instruction set, could that theoretically like outperform the RISC-V?
Yeah. Okay. So I have a couple of things to say about that. So it's exactly the right question to ask. Okay. And I think here's my hot take, right? Like, I don't expect people to agree. I expect most people to disagree with me, but that doesn't change my opinion, obviously. So, as time goes on and we get better at designing snarks, the ZKVM prover cost profiles match up closer and closer and closer to real CPUs. Okay. So, I'd say before Twist and Shout came out like 3 weeks ago, okay, I'd say that this was the biggest gap between the cost model of actual snark provers and real CPUs. So you know the primitive instructions in something like Cairo are defined, to like kind of each primitive instruction can kind of directly be implemented with like one constraint or something, right? But it turns out via lookup arguments that all the RISC-V instructions can be implemented like almost as efficiently. Right. And so, that kind of already, proved in my mind, not that I expect everyone to be convinced that, fairly complicated instruction sets are actually just as fast to prove each instruction as, things that were designed to be, faster. They turned out not to be. So before Twist and Shout, I would say that the biggest gap that remained between ZKVM provers and actual CPUs was the following. On actual CPUs, you have some very small but very fast memories, right? So you have 32 registers, and then you have L1 cache, which is a few kilobytes, and like a read into L1 cache is a couple CPU cycles, and that's it. Then you have L2 cache, which is 10 times bigger or something, and a read into L2 cache is several times slower than a read into L1 cache. And then you have L3 cache, and then you have main memory, right? And our memory checking procedures for snarks didn't look like that, right? So like the provers were kind of just as fast or slow, no matter how small or big the memory was. The provers didn't get any faster if the memory accesses were local in any way, but real computers do get faster from local accesses, in part due to caching. But then Twist and Shout kind of changed that. Like Twist and Shout get faster for smaller memories. Actually, the prover is faster in Twist for local memory accesses. And it doesn't, is it literally the same as CPU cost profiles, with their L1 cache and L2 cache? No, but it's closer. And I think it might be close enough that, like basically tooling that optimizes for CPUs is now essentially more or less optimizing for provers as well, snark provers. And then even if I'm wrong about that, I would say to the extent that we keep making any progress in snark design, it's very likely that the CPU cost model and the snark prover cost model just keep getting closer and closer together. I could be wrong. We could have some weird property of snark provers that comes about in some future snark and kind of stays there forever, and kind of tailoring your VM to take advantage of that really weird property of snark provers just gives you orders of magnitude speedups. I mean, I can't rule that out, but I would personally be shocked, but I don't think that's likely, is my take. Other questions?
Nope.
Great. Okay. All right. So let me say a little bit about fetch, decode, execute, and then we'll get into the proof systems. So let me see. I'm just going to pull up. This is what I always find hardest to explain about ZKVMs. It's not the ZK part. It's just what is the VM doing every cycle. So let me just pull up some notes I gathered. All right. So yeah, I'll explain RISC-V, but again, like all VMs, operate in a relatively in the same high level way, including the snark friendly ones. So there's something called the program counter, I think this is just like a register that, like a memory cell basically, that stores like which, like, line of the bytecode, which instruction in the bytecode to execute next, right? So this bytecode, right, it's literally like a list of, I visualize it as just like 32-bit lines. So each instruction is just specified by 32 bits. So, like line 1 is, 32 bits, line 2 is 32 bits, line 3 is 32 bits, and each line is like an instruction. Okay. And so the program counter just tells you like which line of the bytecode to read next. Right. And so yeah, it's like the address, into the bytecode to read next, and then what the VM. So at each cycle, what the VM will do is just fetch fetch that line of bytecode. So that means just read that line of bytecode. I think this term line is not standard. That's my personal terminology, so I'm probably embarrassing myself. Maybe fetch that instruction out of the bytecode. Again, I'm not totally sure what the people who have actually been trained in computer architecture say. And then I guess typically you would then immediately increment the program counter by 4, which would basically tells it to point to the next line. But this will have to change if it turns out that the instruction you just fetched was a branch or jump. Okay. And so maybe I should have presented like increment the program counter as something that happens, at the very end of the fetch, decode, execute cycle instead of near the beginning, but hopefully it's not too confusing. Okay. And so now that at this point, we've sort of, just read the instruction the computer program is supposed to execute next. So now we, that's 32 bits. Now we have to figure out like what does this instruction actually mean? Okay, so like, I think these instructions, I feel like, completely out of my element giving like a computer architecture seminar, but, I think, a bunch of the bits in it are going to tell you, literally just like which primitive instruction to execute. I think in RISC-V, there's, I don't know, 50 primitive instructions or something, although a lot of them are very similar to each other. So, so log base 2 of 50 bits would be just giving you the identifier of the primitive instruction. You then it's going to tell you like which registers are the inputs to the instruction in. So in RISC-V, the inputs are typically called like source register 1, which RS1, and source register 2, RS2. And which register should you write the result of the primitive instruction to? So that's called RD, and some other stuff. And so the VM will kind of figure out just understand this information that's sitting in the instruction it just read out of the bytecode, and then it will go and actually execute the instruction. So execute. Let me call this INST for instruction. So execute the appropriate primitive instruction on inputs, stored in RS register 1 and register 2, and, write the result, to register RRD. Okay. And kind of that's it, then it'll move on to the next cycle. But of course, there's, I've missed some stuff. I've simplified some stuff. So, for example, the instruction might actually be load or store. The non-load and store instructions. They're things like add the number in RS1 to the number in RS2, or take the bitwise XOR of them, or figure out is RS1 less than RS2, and like if so, spit out 1, if not, spit out 0. So these are like the non load and store instructions, and then there's the load and store instructions, which will say something like load load from memory, from RAM, like the value stored at cell, whose address is in RS1, or it might, rather than load, it might say store, store to RAM, the value stored in RS1, and RS2 has, the cell of RAM that it should be, stored in or whatever. And then you have, the jump and branch instructions, which, are going to change the program counter to not just be, the line following the one you just read, but instead somewhere else in the bytecode. So that's what a VM does, just over and over again. Fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. Questions?
Yeah, someone's coming up.
Hello, can you hear me?
Yep.
Yeah, great. No, I just wonder. I just wonder, why do community, uh, uh, why do we model a hardware computer in ZKVM, and I never saw an attempt of modeling any uh, existing already existing VMs that are which are computational models on itself, like Java, like Lisp, or something like that.
Yeah, great question. So there are projects that have looked at things like that. Lisp was targeted by Lurk, which was renamed to Arguments, for example, although I believe they were targeting like a variation of Lisp that was meant to be snark friendly again, like where, like addition was finite field addition, rather than, machine addition or whatever, stuff like that. And so, there's not wide agreement that this VM thing is the correct thing. Or I should say there is at a minimum some disagreement on the point. My personal take is it does seem so far that like snark prover profiles just seem to match up close enough to actual hardware that the kind of VM you would want to run on actual hardware, just through some kind of miracle of matching of cost profiles, is also pretty good to snark prove. But again, I guess I should just stop there. That there's not full agreement on that opinion. Was that a clear enough answer?
I guess so. I mean, I mean, why did I get this idea at all? Is that it sounds cool if such a VM or hardware processor could have just a mode in it which could allow to issue a proof with the computation that it was working on with some small price over the computation itself. That was the thing.
Yeah. So
that led me.
Yeah, so I guess that's the dream, is forget ZK, for privacy. Like the dream is like anytime any computation in the world is done, for some tiny extra price that no one cares about, it comes with a proof that the computation was done correctly. I don't, I think that that's a pipe dream. I think, the ZKVM provers will always be at least like 1,000 times slower than running the computer program kind of natively, and we can talk about what that at length too, if people want to. But yeah, what I want to say, I guess Lisp isn't that popular. JavaScript is popular, but is it popular just because people are kind of stuck with it, or is it popular because it's like actually good? Maybe people can debate that. We have these tools to. The funny thing is, like, your laptop runs on like ARM or whatever, and we are so far away from being able to build like a ZKVM for ARM. So the tool chain that like a RISC-V ZKVM will use, it's not reaching this ignoring the millionfold overhead for the prover today, even it's still not reaching the dream that you just literally do whatever the laptop does and then add an extra proof because it just comes for free. By going through RISC-V, we're going through a different computational model than your laptop's intrinsic computational model, which is like a Max Silicon or ARM chip or whatever. So yeah, I don't. These are just the sorts of issues to think about and debate. And I'll stop rambling. I think there's lots of debate still to have on all of these questions.
Thank you. That's for perspective. Thank you.
Other questions? Okay, so I guess let's get to how the ZKVMs actually work. So at a high level, look, all they do is they take they identify a constraint system. You can just think of it as a circuit if you want. Okay, that implements the fetch, decode, execute cycle of the CPU, T times for some like predetermined T. That's it, so and then you apply your favorite snark to that constraint system. Okay, and so the way you should kind of visualize the constraint system, although I'm being super hand wavy because different ZKVMs use different kinds of constraint systems and stuff, but I like circuits. So what I think of is like you take a small circuit, which I call C cycle, which kind of implements just one cycle of the CPU, one fetch, decode, execute cycle. And now, I'm super, waving my hands here because, VMs have random access memory, these loads and stores from a large memory, and circuits like don't. So what does it even mean to, implement memory in a load and store instruction in a circuit? And I'd say like, just don't really worry about it right now. And so, you can just visualize the circuit implementing the VM as just like T copies of this, small circuit. Okay. And so you just, do this T times, and kind of, what comes out of the T copy is roughly, like the final state of the machine. And the reason this is so hand wavy, it really all just boils down to the circuits, the whole memory, the VM's memory issue is that for this to actually work, like what C cycle would have to output, is the entire state of every memory cell of the VM, right? Like, and so, because if this copy of C cycle has to do a read into memory, it needs to know what's currently stored at each memory cell and how is it going to, get that information. Well, that information better be fed to it as an input. That's the only information it gets, the way I've drawn the picture. And so if you just kind of imagine we have magical ways of dealing with memory that get rid of that issue, then this is exactly how you can visualize, these ZKVM, kind of constraint systems or circuits, and we just apply a snark to the constraint system. Now, I think slightly more accurate might be the following, and this is exactly addressing the memory issue. You could also think of the circuit as kind of a squashed version of this one. So this is a very deep, narrow circuit. But instead, what you can do is you can, and we've talked about this sort of perspective before, you can have a circuit that takes as untrusted advice, like the entire execution trace of the VM. So that's kind of everything that happens at each, every cycle, just a list of, every register that was read, every register, that was written, every primitive instruction that was executed, like just a list of everything that happened. And then all the circuit does is kind of check that the execution trace is correct. And of course, like the final cell of the execution trace is like the output of the VM or something. And so then what what the circuit would look like in this kind of, checking perspective is all the checks can happen in parallel. So you kind of like check that cycle 1, in the trace is correct, meaning you read the correct line of the bytecode. You decoded according to the execution trace. You decoded the instruction stored at that line of bytecode correctly. To figure out which primitive instruction should be executed on which registers as inputs, and So now you have this like C cycle circuit, kind of just checking. The first cycle was done correctly, and the next copy laid next to it rather than below it would check cycle 2 was correct, check cycle 3 was correct, and so forth. And then this would sort of be like every step 1 was right, time step 2 was right, time step 3 was right, and then kind of separately you'd have like memory checks, which we've talked about, before, and we just discussed twist and shout, which are exactly protocols to accomplish this. And so these memory checks would make sure that, every time the execution trace, contains a value, purportedly, read from some, from some address in RAM, from some cell in memory. This memory checker like checks, so the whole execution trace has to feed into this thing. This memory checker checks that that value is indeed the value that was last written. So I just say is correct, but by correct I mean every read to memory returns the value most recently written to that cell that's being read. Okay,
What
and so
used in the like actual execution trace, like for the memory.
What was that again?
I guess my question was like when the execution is happening, when you're going through like each cycle, like how is that kind of keeping track of like what value is coming to and from memory? And then it seems like you're also checking that in the memory checking.
Yeah, exactly. So basically the way you think of it is the non-memory checker checks are just kind of assume, so they kind of check correctness, of each cycle in the execution trace. And they're just going to take the values returned by any read for granted that they're correct. So
and are they encoded in somewhere in the trace? I guess
they're just in the trace, right? Exactly. So what's going on is, like cycle 1. Here's the information for cycle 1 in a trace. This is some caricature where I kind of probably get some details wrong, but we'll have the value in the program counter, the purported value, everything's purported according to the prover who committed to this trace. So there's the value that's supposedly currently stored in the program counter. Okay. Then there's, like the 4 bytes, supposedly, stored, let's call this PC, stored at line PC of the bytecode. Right. And then there's, the value, purportedly currently stored in RS1, where RS1 was specified, as part of these 4 bytes. Then there's the value, purportedly stored in RS2. And then there's the value, purportedly output by whatever primitive instruction is, also, part of the the 4 bytes purportedly stored at the appropriate line of bytecode, by the primitive instruction. when executed on inputs RS1, comma RS2, or really the values claimed to be in them. So that's the sort of thing. This would be like one entry of the execution trace, would have these different fields in it. Okay, and so
this thing was like, I guess, where does where are the memory values getting?
Great. Okay, so everything I said here was like registers, but registers are part of memory, and so let me answer, just looking at the registers real fast. So when I said this is field of the execution trace is the value purportedly in the program counter. Okay, how do you still have to check that was actually the value, that was currently stored in the program counter. That is a read into a special memory cell called the program counter. So, that's ultimately going to get checked in the memory checking procedure. So similarly, when, this entry is supposed to store is purportedly the value currently stored in register RS1, this check over here is just going to take for granted that indeed that is the value currently stored in RS1. We have to separately check that that's true with memory checking. Okay. Okay, so that's the register stuff. And then, memory comes in when the instruction, that you're supposed to execute is actually like a load. So if the 4 bytes you read from the byte code, if the appropriate subset of those 4 bytes tells you this is a load operation, okay, then a load operation says it'll be load, followed by which register to store the result of the load in. I guess that's RD, followed by like which cell of random access memory to actually read. So let me call that, I don't know, just like address. Okay, and so and then the value purportedly like output by this instruction is going to be in the execution trace, and so that value will just be there. Let me just call it RV for read value, there will not be any check applied in this part of the constraint system to confirm RV is correct, to confirm that RV is actually the value stored at that cycle in that particular memory address. That gets checked separately in the memory checking procedure. Does that make sense? So it's kind of like you have two kinds of checks happening in the constraints. One kind of check just kind of takes for granted that every read value is correct. It just doesn't worry about it. Just make sure everything was done correctly, assuming all the read values are correct. And then completely separately, we confirm that indeed all the read values are correct. Was that clear enough, Abhi?
Yeah, thanks.
Okay. Other questions?
I was having a quite similar question. Indeed. Am I correct that no communication are needed between both types of the checks?
Yeah. Okay. So now we can. No communication is needed. Yes and no. So now I might say a little bit about how the memory checks are done. I mean, we just saw twist, so that is a new way to do the memory checks. The old way of doing the memory checks, one is Merkle hashing, which is very expensive in snarks. There you can kind of almost act like the memory checking is not a separate thing. There every read to memory is accompanied by a Merkle authentication path, kind of confirming that the read is accurate, and so one can instantly just confirm that the authentication path is valid. But that's very expensive because then you're doing hashing over and over again inside these constraints. The other approach would basically, typically, not always, it would kind of resort the reads, right? So like scattered throughout this execution trace are all of these read values, so there's like a cell address and then a value that's purportedly, the value currently stored in that cell. And so the memory checking procedure, what a lot of them do is they have the prover commit to a reordering of all those reads, reordering of all the address value pairs that you want to check, where now things are sort of grouped by memory cell. And once you group them by memory cell, it's kind of relatively straightforward to make sure that everything is kosher. That a given value is indeed the value most recently written to that same cell. Because once you kind of put everything that hit that cell together, life is pretty simple on the checks. So that's where the communication comes in. Is you do have to make sure that communication, meaning information shared between the memory checks and the other checks. You have to make sure that the kind of group by memory location thing is indeed a reordering of all of the reads in the actual execution trace. And so the way this would actually work then is the prover is not just committing to the execution trace, but is also committing to sort of like a reordering of the reads in the execution trace. And then you separately have to check that this is indeed a reordering of the reads in the execution trace, but that's just a permutation check, which we've talked, several times about how you can do that. Did that clear things up a little bit?
Yes, it did. And speaking about twist and shout, uh, is it like totally separated to the extent that it could be done by two parties on the same execution trace?
How do I want to say this? Something like twist and shout, what that would do is so the prover, okay, so I guess it's easier. Let's talk about twist, because that's read write memory, and that kind of maps the most obviously to VMs, because VMs have, the VM itself has read write memory. People call it main memory or RAM or whatever. So in twist, the prover would commit to some extra stuff, but that extra stuff is not a reordering of the reads and the writes. Instead, it is just write increments. Meaning, every time I do a write, like let's say I say, write value, write value. I don't know. I'll make up a value 17 to cell, whatever K. So the twist prover commits not just to 17 and K, but also to the value currently stored in cell K minus 17. So the increments, how much did value K just change by or whatever. Or maybe it's 17 minus, I guess it's negative this, but whatever, you get the idea. So there is, the prover in all of these ZKVMs is always committing to at least a little bit of extra data beyond just the raw execution trace. That extra data is there to kind of help with the checks. And so twist is no different, but the amount of extra data committed in twist is much less than in a lot of alternatives. Maybe I'll put it that way. Was that a little bit helpful, or did I answer a question you didn't ask?
It is another question. It was answer to another question, but it was interesting
Okay.
very much. I mean, what I meant is if two parties if we have imagine we have two provers which have exactly the same execution trace with this additional stuff, I don't know, and it's committed and so on. Could one of them do the proving of the logic part of the cycle, the proving for the cycles, and the other one do the memory check, and would it be okay, or do they need do they need to communicate uh, during the proven during
Yeah.
the proven?
Yeah. I think basically you can just do them totally separately. So there might be some subtleties like, how do I want to say this? So for some of the memory checking arguments, right, the prover has to have already committed to the execution trace and the reordering of the execution trace before choosing or learning via fiat shamir a random challenge, like a random value used in the memory checks. It's like the memory checks are randomized. So it's a big problem if the prover knows the randomness that's going to be used in the memory checks when it commits to the execution trace or the reordering thereof, because then it can just mess with stuff, and it would in a way that's tailored to the randomness that's going to be used in the randomized checks, and they pass the quote randomized checks, but the prover's just lying. So and in these memory checking arguments, often after the prover then learns the randomness to be used in the randomized checks by fiat shamir, then the prover has to commit to more stuff. Okay, so I'm just trying to flag. I guess it's a little bit. The question is maybe a little bit informal, already, but so roughly the two kinds of checks can be proven completely separately. But depending on the machinery used to do the memory checks, you might need like a very precise commit and then fiat shamir and then commit again situation going on. Twist and shout actually get rid of that issue completely. But anyway, okay. Hopefully that was enough of an answer.
Yeah, it's very insightful. Thank you.
Okay, other questions?
Sorry, can you hear me?
Yep.
Yeah, so I just wanted you to elaborate a little bit on the question I had for a while, and that is, what's the main issue with this ZKVM? Is that these trace checks, or I would say memory issue overall, because in classic snarks we don't have this trace at all.
Mm-hmm.
We'll only commit to values, and ZKVM on the contrary does have this, but it allows us to enhance programming experience. So is the main drawback of ZKVM is memory issue?
No. So actually, surprisingly, it's not memory. We now have very efficient memory checking procedures, and they've actually been pretty efficient for a while. Twist and shout are yet another level of efficiency. This new work that came out recently, and so that's not really where the proving overhead is coming from. As all the ZKVM projects struggle to try to make the prover faster.
I would just want to briefly make sure we distinguish between two different types of memory that are happening. So one of them is the memory that exists as part of the computation that we're trying to prove correctness of, and then separately there's the memory requirements of the prover that are running these.
Yes, great, exactly. So we have very good, efficient procedures for making sure that the VM's memory is maintained correctly, in the execution trace, which is committed by the untrusted prover. All of these snarks are extremely memory hungry in terms of how much memory does the prover use. And I'm going to talk about that issue shortly. But let's ignore that right now and just, focus on how slow the prover is. And so you can ask, where does the slowness come from? Why is it so slow? And so the question was is the slowness, is the bottleneck mainly dealing with the memory checks or, the correctness of the execution trace?
Yes,
Yeah.
Exactly.
Yeah. And so I'd say correctness of the execution trace, I guess. The irony is, I think that's a kind of a misleading answer. Okay, so if you actually look at Jolt's runtime today, Jolt's prover time is something like 25% on execute. The just making sure each primitive instruction was executed correctly, it's like 25% on RAM, like proving correctness of RAM, region writes to memory. Okay, and it is like, say the remaining 50% is sort of on like the fetch decode stuff, which is a little bit surprising because you think fetch and decode is kind of very simple. Just read one line of bytecode and kind of figure out what that line says. But actually, kind of, there's a lot of stuff in each line of bytecode, even though it's only 32 bits. So there's like which primitive instruction to execute and what are the source registers and what's the destination register. So just like kind of splitting those 32 bits into, those 4 or 5 different fields or whatever is actually, like just as bad as executing the primitive instruction, or maybe even worse. And so if you look at this, it looked like, well, there isn't one particular bottleneck. Like everything the VM does is like roughly the same, order of magnitude in cost. So I think the right answer to your question is the following. The VM abstraction itself is just can introduce a ton of overhead. All right, and I think it's clearest to think of a particular example. So let's say matrix multiplication. Okay, so a computer program for matrix multiplication, is like the naive algorithm. It's like 3 nested for loops that multiply n by n matrices. For k equals 1 to n, like the output matrix is initialized to 0, and like plus equals what is it, aik times bkj. All right, and so for something like this is a straight line. If let's say that addition and multiplication are over finite field natively here, just to make everything as snark friendly as possible, right? This is a straight line algebraic program. This is, the nicest possible thing for a snark to prove. Okay, so, like the way to prove this, there's actually much better ways to prove it even than this. But like one way to prove it is to just like take an arithmetic circuit that directly implements this algorithm and then apply your favorite snark to that circuit, right? But if you go the ZKVM route, you're gonna, the overheads are going to be so much higher than that, right? Because here we have, there are n cubed steps here, and like rather than just doing like one multiplication and one addition for each of those n cubed steps, we're gonna, n cubed times or more or whatever, like read a line of bytecode and decode that line of bytecode and then execute, the multiplication instruction or the addition instruction, and then, increment the program counter, and then, do it all again and again and again. So like rather than just one addition and one multiplication, like for each of these n cubed iterations, we have a read into bytecode, a decode that read into bytecode, and execute a primitive instruction. And so that's where the overhead comes from. And so, like in general, it's no overhead at all, in the sense that, we ultimately run our computer programs on, actual computers, and they do fetch, decode, execute or whatever. But for things that could have just gotten turned directly into a circuit with no fetch, decode, execute ever, because we know in advance exactly which instruction gets executed at which step, then all that overhead is horrible. Was that a little bit informative?
Yes, the intuition is extremely helpful. So, can I paraphrase your answer with proving with the KVM, we just don't have enough information of the executed program, because we just need to prove instruction by instruction. But on the other hand, we have classic snarks that uses the knowledge of that deeper meaning of the program, and allows to commit only to essential things.
I think that's exactly that correct. Yeah, and to what extent it is, how special is something like this? This matrix multiplication thing is a bit of an open question. But yeah, that's right. Like there's a lot of special information about this particular computer program. Means you don't have to call, fetch, decode, execute every step. That if you go through a VM abstraction, that abstraction itself forces you to do that extra work. So you're right; it threw away the information that was specific to this program. And there are efforts to glue the two approaches together. You see this in Sino is a paper by like Scroll. I don't know to what extent it's implemented, but they kind of are trying. It's one component of that work. They want to look for parts of computer programs that you can kind of turn directly into a circuit like this. And then for those parts of the computer programs, they will not do fetch, decode, execute. They will just have a circuit and like prove the circuit directly. So there are efforts to kind of, bring back in that information and, glue the two approaches together or whatever.
Yeah, that was very helpful. Thank you very much.
More questions?
Yes, speaking of extremely useful, extremely helpful intuition, it just hit me when you were describing all this that actually this ZKVM approach ditches, it liberates us from the limiting nature of the circuit approach. I mean that you can have different numbers of different limit of loops. You can have branches and so on. Is it a true attitude? Is it correct, or does this 50% overhead just could? I mean, it just hides the same limitations that we would have with a specialized circuit.
Yeah. Yeah, no, great question. I think you're totally right. So it does liberate you from that stuff. And my intuition for what's going on is the following. So people like to say, circuits can't execute loops. You have to unroll all the loops, and you need like a predetermined iteration bound to unroll the loop, right? And here I just said, so VMs don't have that problem, right? But I also said you just turn the VM into a circuit and you're done. So what is going on? What is going on is a VM is really just like a master loop. It's for I equals 1 to t, fetch, decode, execute. This is a VM. And so we do have a loop. We are unrolling it. We do need like a fixed bound. So what I'm saying is like unroll this loop into a circuit or a constraint system, and then just that's it, apply a snark to that circuit. So the magic is that fetch, decode, execute is able to here's where I start rambling, babbling a little bit. It's some kind of like I view the VM abstraction as some kind of reduction from all these branches and stuff that we think circuits can't handle to a single master loop that the circuit can handle because it's it has a predetermined iteration bound. Now, as we just discussed, this does come with major overheads, but I don't think it's this like 50% thing that's the big deal. I think it's just having to fetch, decode, execute a primitive instruction over and over again is really the big deal. And it is magical. It does come at a price. So there's no, it's both magical and it comes at a price. The price being, if you run a computer program like this, you're going to do all this fetch, decode, executing stuff that is totally unnecessary. Was that helpful?
Yes, thank you.
Got one more.
Not hearing anything.
Me neither. I waiting still. They've joined the stage, but are not making noise yet.
Okay, give it one more second. Okay, I'll just keep speaking, and feel free to interrupt if the technical issue gets addressed. Okay, so I thought I would address a little bit more about how some of the ZKVMs work in their guts, but you do have the accurate 10,000 foot view now, which is like there's just a constraint system. It the prover commits to the execution trace and some extra stuff to make various checks easier, and then the constraints just check that every cycle was done correctly and all the reads to memory were done correctly, and that's it, and you just snark that constraint system. So the whole game of there are 27 different ZKVMs, and everyone's doing slightly different things. The whole game is just to squeeze the maximum efficiency out of this, right? So I'm going to talk about some in the weeds issues with different ways to exactly implement these checks and things like that a little bit. So yeah, so one issue is the following. I shoved a lot under the rug when I said, well, we're going this class of checks is going to go one cycle at a time and make sure every cycle, that cycle in the execution trace was done correctly. Okay, so at each cycle, there is exactly one primitive instruction that gets executed, right? But the prover, no one knows which instruction gets executed at which cycle until the provers run the program, and after it runs the program, then it knows, right? And the verifier, of course, this execution trace is enormous. If there's trillions of cycles, there are trillions of entries of this execution trace, and the verifier is never going to read the thing, so it's committed. The verifier, has no way to look at the whole execution trace. So in no sense can the verifier possibly know at any time like which instruction was executed at which cycle, unless the computer program is super special like this one and everyone knows in advance which program gets executed at which cycle. But in general, that's not knowable. So there's the question of how do you avoid this circuit, which kind of checks correctness of a single, cycle in the execution trace. How do you avoid this circuit kind of having gates that implement each and every primitive instruction, right? It's like at each step, only one instruction gets executed, but we don't know until we run the program which instruction it is. So if we're fixing the circuit like before we run the program, somehow we have to have the circuit prepared to implement every primitive instruction, right? Because once we fix the circuit, if we haven't run the program, we don't know what's the one we need there. And again, even if even after the provers run the program, the verifier doesn't know for each instruction what got executed. So how can you change the circuit on the fly? You'd have to communicate prune away the stuff that wasn't used. You'd have to communicate that to the verifier somehow. Okay, so people have ways around this to varying extents of performance. The way most people do it today actually dates to a paper called VRAM, which doesn't get credit for this stuff. I don't really know why not. And so what VRAM does is sort of you know how I said the way memory checking is often done is by reordering all the reads to group by memory location, and then once you have all of the reads that went to the same memory cell all together, it's like pretty easy to tell is the value returned by this read actually the value most recently written there. Well, it's something similar happens in VRAM and related approaches. So I believe this is what SP1 does. They call it like some kind of bus meaning basically it just means reordering the execution trace. They sort of think of like sending each cycle within the execution trace to the appropriate instruction that was actually executed there. Buses, I guess, send information around from point A to point B. So what they would do is they would reorder the execution trace to group everything by which instruction was executed at that cycle. Okay, and that way, so once everything is grouped, so here are all the time steps where instruction 1 was executed. Here are the time steps where instruction 2 was executed, and so forth. Now, your checker circuit, that checks this thing only has to implement instruction 1. You kind of got rid of all of the extra stuff, all of the unused instructions at each step. And so you do have to communicate to the verifier for each instruction, how many steps executed that instruction. I don't think that's, I actually don't know whether something like SP1 is communicating that to the verifier or not today. This is what VRAM did, and I know like SP1 is doing something, of a similar flavor. I don't know all the details. But, in RISC-V, there are like 50 primitive instructions. So, telling the verifier, this is how many times instruction 1 was executed, this is how many times instruction 2 is executed, and so forth. Well, that's just 50 numbers. Like, that's not a huge, a huge amount of data to append to the proof. Now that would, break ZK if you care about ZK, but we have ways to bring ZK back in. And so that's the gist of, how it's one technique for avoiding executing every, kind of having circuitry to execute every primitive instruction at every cycle. And kind of, again, the key idea is at each cycle, only one primitive instruction is executed. And, there are ways to, kind of prune away all of the unexecuted instructions at each cycle. You just have to be a little clever about either reordering the execution trace or, doing what Jolt does, which is quite different. So that's a detail I wanted to get into. Let me pause, see if anyone has any questions about that.
There was a question about parallelizing the cycle checks. Essentially, is there a dependency between them if like the output of one cycle is used as the input in the next?
Yeah, so there is, and you have to deal with that, and we have ways to deal with that. So yeah, I normally visualize these, like okay, Jolt is just R1CS and lookups. So the constraint system, the circuit, that's really what I mean is R1CS, rank 1 constraints and lookup constraints, which are kind of a more general kind of constraint or something. And so I generally like to visualize the R1CS and Jolt as follows, so there are 3 constraint matrices, but let's just focus on one of them. So we have 80 constraints per cycle. Right. So to first approximation, I visualize, I guess this, whatever. I was going to make the matrix squarer than fine. Brain is totally broken. Let's just end the matrix here. Okay. So it's this, first approximation, I consider it a block diagonal thing. So we'd have like, one tiny matrix per cycle capturing the 80 constraints per cycle, right? And, the witness vector to the R1CS, which I call Z would just be the execution trace. Right. And so, so Z in Jolt has something like, the constraint matrix is pretty square. It's not exactly, so it has something like 80, values per cycle. And, so I to first approximation, I say like, the 80 values for each cycle are kind of checked for correctness kind of independently of all the other cycles. And if that were the case, it would literally be this block diagonal, the whole R1CS constraint matrix would be truly blocked out, these little 80 by 80, constraints along the diagonal, and that's it. Everything else would be zeros. Okay, but it's not quite true because I think it comes in maybe mainly for the program counter, but you have to make sure that like the program counter at the end of cycle I is the same as the program counter at the start of cycle I plus 1. Okay. And so that introduces like, just a little bit of off diagonalness here. And we have ways of dealing with of this. So yeah, maybe I'll just stop there. I won't go into the weeds. But yeah, so the performance wise, I'd say these provers behave the same as they would if the constraints literally were block diagonal like this, and you didn't have this like these linkages between adjacent cycles. It is an issue you have to deal with, but we can basically deal with it with no performance overheads. Are you? Is that a satisfying enough answer?
Should it be +4 instead of +1?
So this is cycle I+1, but typically what would the new program counter value would be old program counter +4. So here we're advancing one cycle. The program counter, unless it's a jump or branch instruction, as you move from one cycle to the next, typically it's a +4. That's how they differ. So kind of two separate things. Okay. Other questions? Yeah. So in this caricature, you're totally right that like there should be some little like cross cycle checks. And so this picture is a little bit oversimplified. You're right about that.
I think there's a question about kind of how GKR is used in Jolt and other ZKVMs.
Okay. Yeah. Great. So it depends. So in Jolt today, GKR is only used in a very limited way. So in the memory checking that we use today, there is a grand product. So that is you take, this is done to do the permutation to make sure, well, Jolt doesn't do reordering of memory, but you have to make sure that two committed vectors are permutations of each other. And the way you do that is by subtracting a random value from each entry of each vector and producting all those together. Okay, and so you have to product a ton of committed values together. And the way Jolt does that today is we have take a binary tree of multiplication gates to compute that big product, and we apply GKR to that tree, and you can optimize it, GKR for that particular circuit, which is what I did in some 2013 paper, and that's what Jolt uses today. After we switch to twist and shout, GKR will just not be in Jolt at all. Twist and shout get rid of the grand product, so it'll get rid of GKR. Now, another ZKVM that is using GKR today is Sino from Scroll, which isn't fully built, I don't think, but it is in progress. And they use GKR at the other extreme, where they will literally have a whole circuit that implements all these checks, not just the memory checks, and they just GKR the circuit. Okay, and then at yet another point in the design space, there are other projects like Starkware that is sort of more similar to Jolt. It's bringing or Jolt today, but not similar to Jolt after Twist and Shout get implemented. Starkware in their lookups only, as far as I know, are using GKR for the grand products, although they're using different lookup arguments, so it's really a grand sum, but whatever. Yeah, so there are different ways you can use it. My view actually is, since I'm just sharing, opinions willy-nilly here, I prefer lookups, right? So my opinion is the following. If you use GKR, you are forcing the prover to correctly evaluate a circuit gate by gate. Okay. Now it's nice where it's minimizing the amount of data the prover commits to. So that keeps the prover pretty fast in GKR. But there's still work happening for the prover for each gate in that circuit. And actually, you can think very clearly about how much prover work is done. It's if you take the state-of-the-art GKR implementations, it's like 6 field ops that the prover does per gate in that circuit. Okay. If you use a lookup argument, okay, the prover is much freer. you are not forcing the prover to evaluate each primitive instruction by evaluating some circuit gate by gate. Okay. Instead, what the prover does is it's just committing to, the claimed output of the instruction. It doesn't matter how it got to that output. It did not have to go through evaluating this particular circuit gate by gate. And then it does like a little bit of extra work to prove that, that committed output is correct. And if you work it out, like with like shout as the lookup argument, I think it's like the shout prover does something like, I don't know, 20 field ops or something, like per RISC-V primitive instruction evaluation, right? Maybe 20 is a little low. Maybe certainly it's less than 100 or whatever. Let's say it's 100. I'd have to look it up. So, but 100 field ops. This is the same as a circuit, like GKRing a circuit with 100 over 6. What's that? Like 15 gates. Okay, and that's assuming that the circuit has no untrusted advice inputs. Typically, to keep circuits small, the circuit takes some untrusted advice inputs that have to be committed, and that's like extra work for the prover on top of that. All right, so it's here. Let me summarize. So in my view, like the only possible primitive instruction that you could define where it would actually be better to use something like GKR rather than lookups would be, if your primitive instruction like operates over the finite field directly and like takes, its inputs and like raises it to the fourth power or something, right? Then maybe you should take the circuit that, we call this Y, so that, that squares Y twice or something like that, whatever. Yeah, that squares Y twice to get Y to the fourth, right? Like, so if you can, like the only kind of thing that you can implement in a circuit with, under 15 gates, and no untrusted advice is, like direct finite field arithmetic, right? And so for really anything, you should be using lookups and not GKR. So, GKR is a beautiful protocol, but it's kind of at an extreme. It kind of, in its purest form, the prover commits to nothing at all. Okay, and like that minimizes the prover's commitment cost, literally makes them zero. But as a side effect, the prover's field work goes up, right? Like the right place to be is like have commitment costs be low enough that they're not a bottleneck, but not zero. And then, make the prover's field work as low as possible given that. All right. And that's where lookups live. With lookups, the prover commits to a little bit of extra stuff for each lookup. Actually maybe not even, anyway. And, yeah, so, that kind of took the answer in a direction that maybe, wasn't, expected or desired. So apologies for that. But so that's the gist. So different ZKVMs use GKR in different ways, from kind of the whole thing being built at GKR to GKR being used exclusively for grand products to no GKR at all. And Jolt lived in right now as implemented, it lives in the like let's use GKR just for grand products, but pretty soon it's not going to have GKR anywhere. Other questions?
Some people are typing.
Okay. Well, I guess I'll continue a little bit and then, interrupt, please. Okay. All right. So let me see what else I want to say. Okay. So I guess there's only two more things I want to discuss. So let me write them down so I don't forget them, and we'll see how quickly I can get through them. So one I want to discuss is prover space. And the other thing I want to discuss is, I guess, jolts a little bit and how it differs from other ZKVMs, I guess. So let's talk about.
interrupting. So the question came in. How do ZKVMs prove in operations with circuits handle the overflows?
Yeah. So now I can tell you how Jolt does it. And yeah, I guess other. Okay. Well, all right, so let me tell you in general. So other ZKVMs, how they do it. Let me start with that. So I guess I'm going to repeat the question in different words, so you can confirm that this is indeed what you're asking. So like, let's say you want to add X and Y. You're saying like, well, you could just, let's say X is a field element and Y is a field element. Okay, in RISC-V, these would be 32-bit data types, and so let's say we're representing them as field elements in the natural way, just by binary representations or whatever. And so if that's the case, then you're like, well, okay, I can just do, like X plus Y in the field. But the question is, RISC-V says, hey, like, if X plus Y is greater than 2 to the 32, you should, subtract 2 to the 32. That is, throw away the high order bit. And the question is, how do you do that? Right? Because, if you're working over like a large characteristic field, X plus Y, there's not going to be any overflow. But RISC-V says, hey, if there's overflow, throw away the bit. So the question is, how does everybody deal with this? If that's not the question, please say, interrupt me, but I'll tell you how people deal with this.
And that's what they're asking.
Say again?
Confirm that is what they're asking.
Okay, great. Okay, so most ZKVMs today will actually store X and Y via byte decomposition. Okay, and they're actually forced to do this. They really have no choice. And the reason is most of them are working over a field of characteristic strictly less than 2 to the 32 today. Which mean, they're working over like a 31-bit field. Okay, which means you can't even store a single RISC-V data type in a single field element, right? Like you cannot, RISC-V can represent the number 2 to the 32 minus 1 in a single data type, and the baby bear or Mersenne 31-bit field just can't store a number this big. So everything is stored actually via byte decomposition, and so they sort of just do everything byte-wise. And as a consequence of doing everything byte-wise, they wind up explicitly computing the overflow. I'm sort of I'm inferring. I haven't looked at everything. I know that they do the byte decomposition, and I think then if you just implement base 2 to the 8 addition, you wind up computing the overflow naturally as part of that, and then you just get rid of the overflow. Okay, I'll tell you how Jolt deals with this, which is we would do the addition directly in the field. Okay, so Jolt would not do a byte decomposition. At least if it does today, it does a lot of byte decompositions for other reasons. Those reasons go away after we switch to twist and shout. So in the future, it will not be doing byte decompositions at all. And so X and Y would be stored as just like a single field element each, and we would just do the addition in the field. Okay, then what we would do is we would then do a lookup of address X plus Y in a table, whose zth entry stores the high order bit of Z. The 33rd bit of Z. So it's a table of size, 2 to the 33 or whatever, whose zth entry stores the high order bit of Z. Okay, and so that tells us the overflow, and then we can just subtract off the overflow. And so we do this for multiplication too. We work over this is why I think working over fields of, Goldilocks and bigger is like super nice for ZKVMs. Actually, this right here is if you want to do machine multiplication and Jolt, we can just do that multiplication in the field. Okay, like no one else can do that because they'd have to do everything byte-wise and it's a mess. It's terrible. We just do the multiplication in the field and then we use a lookup, a couple lookups to identify the overflow and subtract it off. And that's it. Like this is so nice. So, I'm really hoping, and I think lattice stuff might give us a path forward. I'm really hoping to get like post-quantum analogs of Jolt, or not be stuck with 256-bit fields without having to go to binary fields. Because over binary fields, everything is much worse than I just described here. So I'd love to keep working over, Goldilocks and up in terms of field size. It makes it, identifying overflow like just the cleanest, simplest possible thing. Did that make sense?
If the field size is greater than 2 to the 32, do you still have to do the bit decomp for like a 2 to the 256 field size?
Yeah, you need to do it to the byte decomposition. No, Jolt will not be doing byte decomposition.
For the circuit ZKVMs, I'm not sure if it's for something different.
Okay. So if the ZKVMs that today use 31-bit fields instead used a 256-bit field, the question is, will they no longer have to do these byte decompositions everywhere? That's the question.
I'm not super clear with the question.
Okay, all right.
They said yes, that's it.
Okay, I would say they might still have to use it, but if so, it'd be for different reasons than today. I think they probably still would want the byte decompositions to be able to use lookups, right? Like if if you're not using sum check, you definitely don't want to be doing lookups into like super giant tables because you're going to pay a prover cost that grows with the table size. And so you're kind of limited to tables of size at most like 2 to the 16 or something. And so that brings in byte decompositions because like if you want to do anything interesting on 16-bit inputs, well, that probably those are 8 bits from your first argument to your instruction and 8 bits from your second argument to your instruction. And so they the byte decompositions might stay even over a big field because of how lookups work, especially if you don't have a sum check based lookup argument. And there might be some other reasons too, that they would stay. But the most obvious reason would go away. The most obvious reason is that a 31-bit field literally just cannot represent a RISC-V data type in a single field element. Okay, other questions?
Yes.
Okay.
Thank you. You already started to answer my next question about this giant lookups, and I'm wondering if the lookup table you mentioned for the overflow check, is it virtual one like you were describing in previous sessions, and also why is it to the 2 to the 2 to the 32? I can not get in this.
Oh, sorry. So 2 to 32 is just coming in because like RISC-V's primitive data types are 32 bits, which means any value stored in a RISC-V memory cell or register.
It's a lookup table of the every value of the type.
Sorry, I didn't quite catch that.
I mean, it's a lookup table which holds every value possible in the type.
Oh, yeah. So, right. So here, Z can be as big as like 2 to the 64 if X and Y are each, as big as 2 to the 32. And RISC-V says, so if Z is 64 bits, RISC-V says, hey, identify, like, just keep the low order 32 bits, and throw away the high order 32 bits. So, this is what we want to identify. So the lookup table, the simplest thing to do would have the prover commit to, Z low, Z high, as individual field elements. Okay. Add a constraint, confirm by adding a constraint to the R1CS, right? That, Z equals, Z low plus 2 to the 32 times Z high. And then, confirm via lookup that Z low and Z high are both in the table, storing field elements 0, 1 up to 2 to the 32 minus 1. So that's how we identify the overflow and get rid of it, how we identify Z low. Did that answer the question?
Yeah, absolutely excellent. Thank you.
Yeah. Great. Another question?
Yeah, I think there's one more coming. He's on stage waiting for you to ask.
No. My question was already answered. That was my question. Thank you.
Okay, great. Okay, cool. Yeah, so I guess I was about to go into these two things, and then we got that nice question about identifying overflow, which I'm happy was asked, because I think that's raised some important details that differ between ZKVMs. Okay, let's talk about prover space real fast. Looks like my pen needs to charge for a second, so I'll just speak for just a little bit. Okay, so if you apply something like Jolt today, nothing special about Jolt here, all the ZKVMs are like this. So if you sort of apply them directly, naively, like to let's say 1 million RISC-V cycles, okay, they're going to take gigabytes of space. I think Jolt, if you do 2 to the 24 cycles, which is like 16 million, I think it might still be above 100 gigs of space for that or something. Okay, so what people do today is, to keep the prover space small, is they will split an execution trace of, if there's 2 to the 40 cycles in the execution trace, they'll split it into 2 to the 20 shards, each of size 2 to the 20 or something. So, you'll split it into shard 1 up to shard, T over shard size, where T is the number of cycles. And typically the shard size is like 2 to the 19, used to be 2 to the 20, and people tried to go lower recently. And you prove each shard kind of separately, and then you recursively aggregate the proofs. And that way the prover only has to be applied kind of monolithically to kind of, 1 or 2 shards at once. And that keeps the space under control. Okay. Now, this brings in a challenge which is underappreciated. Okay. So that is the shards cannot be proven completely independently. And there was a question about, are there kind of checks that have to cross cycles of the ZKVM, which is getting at the exact same issue. Okay. And so the key issue is, how do you make sure that, like, this confirm that the state of the machine's memory, the state of RAM, okay, at the end of shard I is the same as the state of RAM at the start of shard I plus 1. Okay. And this feels like it's just a headache, and in the end it is. But in fact, people have struggled with this and have wound up doing things that I think are not performative as a result. So, what I want to say. So the ways people have done this, which I think are not super performative, actually. So RISC-0 actually uses Merkle hashing for memory once you have more than one shard. which as I've said before, is like incredibly expensive. You're every read to memory, you're proving all of these hashes in the authentication path were computed correctly, and so that actually in RISC-0 they've described this in detail, which is great. Every page of memory that gets read, the first time that page is read, anything in that page is read in a given shard, it actually costs over 1,000 kind of CPU cycles to deal with all the hashing. So one read to memory costs, like over 1,000 cycles, whereas for RISC-V, it just costs one cycle. Now they do some caching stuff. So like you kind of pay that, those 1,000 cycles or so for an entire page of memory. And then once you do it, you don't pay that again for the rest of the shard anytime anything from that page is read. So if your memory accesses are very local, this is not a big deal. But if they're not local, it can be a big deal. And then you have to like mess around with the memory accesses of your program to try to get them more local or whatever. SP1, apparently my understanding is they used to be doing kind of this lightweight, fingerprint like permutation and variant hashing, like multi-set checks, permutation checks. But they couldn't figure out this issue, evidently. So I think they actually, based on their recent blog posts about how they try to address the issue, I think before they would prove each shard separately, but then they would not be proving like the memory accesses. They would only be, remember I said there are two classes of checks. There's kind of like, correct execution of each cycle, assuming all the reads were read values are correct, and then separately you check that the read values are all correct. I think the sharding was really only handling the first class, and then all the memory checking was done all at once across all shards. So I'll call that like monolithically, like kind of wasn't sharded. Okay, and that's like really not good for massively parallel stuff. In a sense, it defeats the purpose of sharding, I guess. I'm not actually sure why that didn't create like a giant space bottleneck. I could be getting some of the details wrong. I'm doing my best from the blog post and everything. So what they've actually switched to is what I'd call non-lightweight multi-set hashing. Okay, so here, by lightweight, I mean like you pick a random field element and then you confirm that like AI minus R, grand product equals BI minus R, where these AIs and BIs are certain vectors that arise from all the reads and writes to memory, and it's just addition to multiplication and or whatever. By non-lightweight, and so this is like a, okay, so you could think of this as like a hash of A, and this has like a hash of B. Okay, but it's not a collision resistant hash, right? Like if I know R, I can easily find like two vectors A and B that are not permutations of each other, but this equality holds. Okay, so what SP1 is doing now, and Nexus also, Jens Groth had some nice optimization to this non-lightweight thing. So I think it's kind of like not the right thing to do because it's not lightweight, but it's been optimized, with some really clever ideas. It's a collision resistant thing. So it's a collision resistant multi-set hash. Okay. And what this means is like every time you do another read or write to memory, this collision resistant thing involves elliptic curves, and you kind of have to, do some Poseidon hash to, get an elliptic curve element and then do some elliptic curve operation or something. And so it's just, it's 5 or 10 times pricier for the prover per read or write than the lightweight stuff. And the benefit of this being a collision resistant hash is it winds up making it really simple to confirm that like the state of memory at the end of shard I is the same as the state of memory at the start of shard I plus 1, by just kind of passing the hash, as inputs, from one shard to the next. The downside is it's making all the reads and writes like, 5 times or more expensive. I guess now Twist and Shout, it's even that difference is going up because we just, improved over the old way of doing things. So I think this is a major issue. I think, where like Jolt hasn't run on very big, instances yet because we don't have the prover space controlled at all. And so I think, we're not planning on doing either of these things in Jolt. There are other ways to address this stuff that I think is, ultimately leads to, better performance properties. So TBD. I thought I would flag the issue. It's definitely underappreciated as like it's something people have really struggled with. Any questions about that? Question?
No, not in chat. Just go ahead.
Okay, so my actually preferred outcome here is to just get rid of the sharding. Okay, I think that if you are doing the sharding, I think there are better ways, to kind of do the linking of memory between, adjacent shards. But I'd rather just not do sharding at all. Like life would be so much simpler. And also I think the security of the resulting snarks would be on firmer footing with no recursion. And you can do this, and we're working on this in Jolt 2, working on it. So if you want to see, there's actually a bunch of papers. It's like known that you can do this. Like with some check-based snarks in particular, you do not need recursion to keep the prover space under control. Like the main point of sharding is prover space, making sure the prover doesn't need like terabytes and terabytes and terabytes of space to prove even like small, program executions. And it's known you do not need recursion to control prover space. But for some reason, no one has really pursued implementation of that. And I've actually, I'm writing up the details, even though it's known the details for Jolt. And it looks like the overheads, like the prover should not really slow down all that much by keeping its space under control without recursion. So this is where I hope things wind up. Life would just be simpler. But, if you are going to do the sharding, I think, there are key issues still being worked out with that approach. Okay. And so I guess the last thing I wanted to talk about a little bit was Jolt, kind of what makes it unique. I'd say, sort of number one, it's based on the SumCheck protocol, as like designed, as SumCheck as like a first order citizen, SumCheck and multilinear polynomials. That gives it access to things like twist and shout, that are like much faster. You like memory checking arguments, so it'll be much faster to like for the prover to prove that, it's maintaining the VM's random access memory correctly and stuff like that. But then the other thing that makes it unique is leaning into lookups. Okay, and so coming back to the constraint systems we discussed before, especially when I came to VRAM. Where did I discuss VRAM? So here must have been VRAM. So I said the way that something like VRAM makes sure that every primitive instruction was executed correctly at each cycle, every time it was executed, is it like, does some group by, which instruction was executed at that cycle to avoid, kind of having the prover pay for primitive instructions that weren't actually executed at a given cycle. But then, for the primitive instruction, that is actually executed, it implements it directly in a circuit. And then you apply your constraint system, and then you apply a snark, for circuits or constraints, whether it's GKR or some kind of Stark or whatever, for air constraints. Jolt doesn't do that. Okay, so what Jolt does is to make sure a primitive instruction is executed correctly. So to make sure that like Z equals, add of XY, well, we already talked about this kind of, like it just does a lookup. Let me switch from add and mult are a little bit different. Let's talk about like, I don't know, bitwise end. Okay, so roughly what Jolt does is it just does one lookup into, the size 2 to the 64 table, whose, XY entry, is the bitwise end of X and Y. Okay. And, today Jolt uses lasso for those lookups. And lasso under the hood kind of does something resembling a byte decomposition for this sort of instruction, although it doesn't do byte decompositions for all instructions. But after we switch to shout, there will definitely not be any kind of decomposition at all. And yeah, and so like this table is huge. Nobody can write it down, but it's a very, very structured table. And so it turns out no one has to write it down. You kind of only have to, materialize the entries of the table that are ever actually accessed. And those, you get purely by executing the primitive instruction, right? So, we do this for two reasons, both speed and simplicity. We talked about speed already. I sort of compared like lookups to GKR, and like kind of doing one lookup into a table like this, I said is about equivalent in prover speed if you're using shout for the lookups, to like applying GKR to a circuit with, I don't know, 15 gates or something. So it's faster than I think, directly proving circuits would be. And in fact, this is exactly what lookups were designed for, is kind of to make something like this as fast as possible. So, I don't quite understand why it's controversial that using lookups to do this stuff is the right thing to do. It's like, this is literally the problem lookups were designed for, was to, do repeatedly, do lookups into the same table over and over again. That's exactly what we're doing here. And so so I think it's good for speed. Okay, but it's also good for simplicity, because you don't have to take each primitive instruction and optimize a circuit for it. You just have to specify the lookup table, and that's just like a much simpler thing than specifying a circuit that computes the same function, as the table. Like, just circuits are more complicated and grosser. So that's Jolt in a nutshell. There's a lot of the same ideas floating around. Almost everybody is doing, some kind of, permutation, checking, for both memory and, elsewhere in the VM. And actually Jolt's getting rid of that with twist and shout, but, today, as of today, kind of everyone's doing that. There's a constraint system in Jolt. It's just a minimal one. There, just like other ZKVMs are built like entirely out of constraints. Although they also use some lookups. So, it's the same stuff over and over again, but I'd say these are the things that make Jolt unique, Suncheck and multilinear, like through and through, and, minimizing the use of constraints and circuits, and doing as much as you possibly can with lookups. Okay, so I can pause here, see if there are any questions, but I think this is most of what I wanted to say today. Any questions?
Yes. Let me to take a moment to formulate. You said that you just described how instructions are modeled are implemented with lookup tables, and it is insightful. It is insightful, and the next question is whether it makes sense to do the same thing with common operations inside the program that we feed into the VM or VM circuit itself. I mean, does it make sense to think about some primitive operations inside the program in terms of similar lookup for getting any benefit, or does it make no sense?
No, it does make sense. I think there are two things I've thought about that seem related to what you're saying. So one is, okay, so there's this notion of precompiles, not to be confused with like EVM precompiles in Ethereum, which I find it actually can be quite confusing. So ZKVM precompiles, it's basically the same as adding additional primitive instructions to the instruction set. And so the idea is, I mean, it's closely related to like, this notion I attributed to Sino of like identifying circuit-like parts of computer programs. So you can, then skip doing fetch, decode, execute over and over again for those parts of the program. So it's like, let's say I want to compute like a catch-check hash. Okay, as soon as I know I want to compute a catch-check hash, right? Like, one thing I could do is I could just implement catch-check in RISC-V and prove I ran on that RISC-V, subroutine correctly. Okay, but that's doing this fetch, decode, execute thing over and over again. When as soon as I knew that it's a catch-check hash that I'm doing, I basically know the next sequence of several hundred or thousand instructions I'm about to do. I don't need to do fetch, decode over and over again for that. So precompile says, all right, I'm adding like catch-check hash as a primitive instruction. And typically the way people implement the precompiles today is they just write down a circuit, for it. So this really, the way I just described things, I made, it sound like Sino just like reintroduced the notion of precompiles, and sort of in a sense it did. The difference with Sino proposal, which again I don't think is like implemented at all, but it would be, I think it makes a lot of sense. Is the proposal would be to identify in a program dependent manner what precompiles to use, and then presumably generate those precompiles in an automated way. Okay, and actually Powder Labs has something where they do something like that. So Powder Labs sort of has like automatically synthesized errors or something like that. So they had a blog post, several months ago. So that's of a similar, flavor or whatever. And so, I do think, look, I'm generally somewhat anti precompiles. I think people have a tendency to just, paper over the horrible performance of ZKVMs by, just grinding out a bunch of precompiles, which are definitely full of bugs. And, people then just use them and, it makes things, 5 times faster or something. And so it makes the prover just like, it speeds things up. But like, if that's how you're getting the speed up, it doesn't scale. As we try to do something general purpose, every time you have a new application, you're going to have to, hand code a new precompile. It's going to be full of bugs. You're going to need an expert to do it. It defeats the whole point of the ZKVM. But if the precompiles are automatically synthesized and formally verified for correctness, then it's fine, right? So I think in the long term, that's what will happen is like, we will have compilers that will take as input, some Rust program or whatever, language is popular in 20 years. And it will do some analysis and figure out like, these are the right precompiles to have for this program. It will specify, output some specification of those precompiles, and then, the prover will prove it ran the program correctly using those precompiles. So that's where I think things will go in the long run. I think it's going to take a very long time to make all that work out. What's one more thing I want to say? Maybe I'll just stop there. So so I think your question of like, does it make sense to like add, lookups or other things, sounds a lot like these precompiles, added in a program dependent way. It sounds a lot like, adding a new primitive instructions, okay, to the instruction set, which is basically the same as a precompile. The last thing I'll add, though, is, in my view, like the right way to design precompiles does not go through constraint systems, right? It's just jolt to redux, right? Like the right way to build a ZKVM is with like lookups, like a minimal R1CS and lookups. Right, and that's the right way to design ZKVMs for both performance and simplicity. And so I think that extends to precompiles too, right? The precompile should not be built out of errors or whatever. It should be, lookups to the maximum extent possible. And, to the extent you can't do everything with lookups, you have some constraints to like glue the lookup, results together. And that's it. So I do think the way people specify their precompiles over time is going to change. Okay, I'll stop rambling. Let me know if that was the kind of answer you were looking for.
Yes, absolutely, and it's very helpful to structure everything in my head. I only wanted to follow up with the question of if I understand correctly that this lookup approach, for example, you mentioned catcheck. So the main struggle to make a lookup for a hash function would be to find this equality Twiddle part in the sum check equation, or am I recollecting and
Yeah,
looking
great.
at the whole?
No, great question. So it's not the EQ twiddle part, because EQ twiddle is that's like a fixed function that's or polynomial that's really fast to evaluate, and that all just works out. So the issue with like a catcheck precompile, the reason it's like not trivial to design one, especially using lookups, is shout, or really like any like sum check based lookup argument, it's going to need the multilinear extension of the table, so the MLE of the table, to be quickly evaluable, right? So like, if the table has size 2 to the 64, actually for catcheck, I guess, catcheck, typically you're hashing 512 bits or something, right? So that table would have size like 2 to the 512, if you were storing like, all possible evaluations of catcheck, that table would have size 2 to the 512. And obviously you can't spend time linear in 2 to the 512 to evaluate the MLE of this thing at a point. So you can hope to do it with more like, about 512 field ops. Okay, the problem is, like, this is what you would hope for. And catcheck is way too complicated. There's no way that's doable, right? So like if we look at the catcheck table, say it takes two 256-bit inputs, and we look at the multilinear extension of that, right? Like there's definitely no way you can evaluate it. Like there's no way you can evaluate this polynomial with, at a point, in 512 field ops, so what you'd have to do to get a catcheck precompile using lookups is you'd have to break the computation of catcheck into pieces where each piece is simple enough to handle with a lookup. So it's like you can't apply lookups, like something like shout, to arbitrarily complicated functions. The limitation on the complicatedness of the function is that the verifier has to be able to evaluate the MLE of the table quickly. And so that's the game, and that's why it's going to take a long time, I think, before we have like really nice lookup based precompiles everywhere. We'd have to have a nice way, an automatic way to take, the code implementing catcheck and break it into simple enough pieces, so you can handle each piece. And by piece, I mean, like one step of a computation or something with a lookup, and then, like glue all the, pieces together in some way, post-process all the pieces to get the final output catcheck of XY. So yeah.
And that's how true zero knowledge VM instruction set will evolve from risk.
Yeah, maybe. So it's possible that yeah. So this thing right here, like what makes a table kind of simple enough to apply shout to? This may be how snark. Yeah, this may be the definition of snark friendly in the long run. Maybe like that's possible. Okay, and so it might be that real hardware has some constraints in terms of what people put in their primitive instruction sets. Also, real hardware, FPGAs, I guess, can be program specific, but anything else, any CPU is not, or whatever. But this whole MLE of the table, being fast to evaluate, this feels like it might be kind of snark specific and not have an analog in the physical world. And then so maybe that is how, you know, snark friendly VMs come in, is like we just develop really good ways of, you know, identifying these pieces that, you know, are as complicated as possible, subject to having their NLEs, you know, of the tables be quickly evaluable. The counterpoint though is, you know, loosely speaking, like I would, very hand wavy, I would describe like what makes an, you know, a table MLE fast to evaluate. Well, typically it feels something like, you know, the, you know, XY entry of the table, you know, is a simple function. I mean this in a very informal way, is a simple function of the bits of X and Y. You know, so typically that you know, that MLE being quickly evaluable, that is equivalent, you know, intuitively to that thing. And X, you know, the output of a primitive instruction being a simple function of the bits of its input is also the kind of thing that makes that like a nice instruction for real hardware. Like it's not literally the same, but you know, if you squint hard enough, it starts to look very, you know, almost the same. So, you know, I'm just rambling and speculating wildly, but you know, it may well be that you know, the ZKVMs and actual CPUs, you know, continue to converge over time. I also could see it going the other way a little bit. No, I'll stop rambling.
It's magical. Thank you.
More questions?
Yeah, sorry to make you repeat things again, but yeah, when we spoke about trace checks, you mentioned that there are things like untrusted advice inputs. I missed the essence of this thing. Can you please repeat what is it?
Yeah. Can you just repeat one more time what part of the presentation this came up during?
Yeah, you mentioned untrusted advice inputs. It was I think it was in the trace checks.
Yeah.
You mentioned.
Yeah. Okay. Sounds good. Okay. So I'm going to give you a example just to illustrate, you know, the basic idea. Okay. So let's say your computer program, you know, calls the division instruction in RISC-V, right? Now your actual RISC-V program will literally run a division algorithm now, or something like that. Okay. But what we do in snarkland, so you know, we want to compute, you know, I don't know, 1 over x, you know, x inverse. So what we do in snark, so yeah, I guess this would be 1 divided by x. So what we would do in snarkland is not run a division algorithm like in a circuit. Instead, the circuit will take as untrusted advice the claimed inverse. So it'll take as untrusted advice a value y, which is, you know, claimed to equal x inverse. Okay, and what the circuit or constraint system will do is it will just check that y, you know, y times x equals 1. Okay, so this is, you know, by having the untrusted advice, by having the untrusted, you know, the prover be able to tell us this y, and then yeah, we don't trust it, but it's just one multiplication to check it's correct. We avoided, you know, computing this value from scratch. That's untrusted advice. And so we avoided, you know, running a division algorithm in the circuit by having the prover provide 1 field element worth of untrusted advice, as, you know, so it has to pay, you know, commit to that, and then, you know, proving 1, you know, rank 1 constraint. And so there are more sophisticated forms of untrusted advice, more sophisticated examples. And so I think this came up when we were talking about memory checking and twist, which is a new memory checking procedure. And so, you know, in twist, if you have an execution trace that's committed, and, you know, now the prover's trying to prove to you that the execution trace is correct, you know, step by step, cycle by cycle. And one part of, you know, one thing you have to check is that, you know, every read to a memory cell actually indeed, you know, stores, you know, the execution trace has the value, you know, that is actually stored at that cell at that time of the execution. You can use, you know, this new protocol called twist for that, but the prover does commit to some extra stuff within twist. And I since I covered Twist like I think last week or 2 weeks ago, I actually briefly today described what that extra stuff is. So there's just some extra untrusted advice to help with the checking of the execution trace. In Twist, this extra untrusted advice is called increments, and basically every write in the execution trace gets one extra value committed. The details aren't important, but gets one extra value committed, which we call the increments. Yeah, and so this untrusted advice is just there to kind of aid in the checking that all the reads and writes were processed correctly within the execution trace. Was that clear enough?
Yeah, I guess so. I also wanted to ask. You mentioned that sometimes they are not as good, but I'm not sure. Did you say that? That they are not...
Well, there was the discussion about like GKR versus lookups, and I was saying that I thought with very few exceptions, lookups are the right thing to do, and so it's possible you're referring to that. And as I was rambling through an explanation of why I feel that way, untrusted advice came up then. So my guess is that's maybe what you're referring to, and I can repeat that real quickly if that would be helpful now that you have the extra context. So GKR is sort of an extreme protocol in the sense that if the input is public, like so the verifier knows the input, right, and you don't have any untrusted advice, okay, then, and this is a circuit, so everything fed to the circuit is known to the verifier, right? So there's nothing committed or whatever. So in this context, the GKR protocol is if you don't fiat shamir it anyway, it's information theoretically secure. Okay, that means unconditional security. No cryptographic assumptions. Okay, so no cryptography at all, if you will. Okay, and that that's an incredible thing, because cryptography is in general expensive. So if there's a lot of untrusted advice, if you want the proof to be short and the verifier to be fast, you can't just send all that advice explicitly to the verifier. The proof has to cryptographically commit to it, and it's expensive to commit to stuff. You commit to a lot of data; it takes time. GKR minimizes the amount of data that gets committed. Okay. In fact, if there's no untrusted advice and the input is public, then literally GKR does not have anything committed whatsoever. Okay. But the thing is roughly that if you allow a little bit of untrusted advice, just a smidge, you can often get speed up. So it's like GKR makes it like zero commitment cost, but then, 6 field ops the prover does, per gate of the circuit. Okay, so it's going to the extreme of almost no, literally no commitment costs, but potentially quite a bit of field work. Okay, and what I'm saying is in the ZKVM context where you're doing the same primitive instructions over and over and over again, this is too far to the minimized commitment cost extreme. It'd be much better to have small commitment costs, so maybe by zero, untrusted advice or whatever. It'd be much better to have small commitment costs, a little bit, and then do less field work. Do less than 6 field ops per gate of a circuit. Okay, and it's sort of GKR was designed. The authors wanted something information theoretically secure. They tied their own hands and said no cryptography. We're not interested in using commitment schemes anywhere, and that led to this beautiful, amazing protocol. But here in Snarkland, we do have cryptography, and it makes while you don't want to commit to too much data because then you're going to bottleneck the prover, it's going to be too slow. it doesn't make sense to commit to zero data. Like you should commit to just enough data. You sort of, I view it as like two costs that should be balanced, right? Commit to just enough data that is not a bottleneck. And then kind of the more data you commit to, it turns out the fewer field operations you have to do. And so you should just equalize the two costs, and these lookup arguments seem to be doing that. Okay, maybe that wasn't clear, but that's where I think this untrusted advice came up.
No, that was perfectly clear. Thank you very much. Thank you. Yeah, I just missed the idea, and now you repeat that, and you now get that. Thank you.
Okay, great. Other questions?
Looks like that's it.
Okay.
What's the plan for next week?
Okay, yeah. So I think next week we'll cover Fry and probably then Growth 16 and then Recursion and Nova. So we're looking at maybe I don't know, another 6 weeks max, probably less. So probably 4 weeks. So yeah.
Awesome. Thanks. See you then.
Yeah. Everyone. Thanks, everyone.
Thank you very much.